Well, good afternoon, good evening, and good morning to those across the pond and around the world. You are listening to Earth Changes TV Radio Hour. My name is Mitch Battros, and I am your host. Join us as we explore the latest breaking news events, which in fact affects us all. Every Tuesday and Thursday from 9 to 10 p.m. Pacific Time, you will hear the latest breaking news and research from the top minds in their respective fields. We will hear from seismologists about earthquakes, volcanologists about volcanoes, climatologists about climate change, paleontologists about historical records spanning thousands and even millions of years. We also invite the brightest minds in the study of ancient text and civilizations, Mayan and Hopi elders who tell us of prophecy and their historical observations, passed on from generation to generation, often telling us with stunning accuracy of today's times. Never before have we seen the two worlds of science and ancient text joined together with such unity and precision, outlining a pathway of discovery. So once again, welcome folks. Here we are live, April 21st. I hope things are going well in your part of the world. I'm very excited about tonight's guest and the subject of the Earth's core. And we will get to that in just a couple of minutes. But first, staying with tradition, we will go to the latest breaking news events of the day. A solar eclipse on the moon, is it's titled. There's going to be a marvelous solar eclipse on April 24th. One problem. Well, where did I see that? Did I see a problem here? Too bad they won't be there this Sunday, and they're talking about NASA is planning to send people back to the moon. Well, that's going to be a great thing, except the target date is 2015. So it looks like they're going to miss this April 24th event. On Earth, solar eclipses happen when the moon covers the sun. On the moon, the roles are reversed. It's Earth that covers the sun. Such an eclipse is a marvelous sight, according to Apollo 12 astronaut Alan Bean, who saw one in 1969. Other things going on. NASA delays earliest shuttle launch date to May 22nd. There's a lot of people keeping an eye on this one, folks. I don't know the exact reasons thereof. A lot of gossip and rumors. We will see how things unfold, so I'm not going to really elaborate so much on that, but let's keep an eye. We're talking about tomorrow, so let's see what happens. Now remember, this the shuttle mission has been canceled since the 2003 Columbia disaster, so this is a huge moment for the space industry. Geologists find a new active fault in Nepal, just what they needed. A Dartmouth researcher is part of a team that has discovered a new active thrust fault at the base of the Himalaya in Nepal. This new fault likely accommodates some of the subterranean pressure caused by the continuing collision of the Indian subcontinent with Asia. And let's see, I think I'm going to cut our breaking news events somewhat short for today so we can have more time to discuss with my guest the Earth's core and everything that goes with that. Just one last thing, Alaska's Mount Spur continues to rumble. Well, this is one of about a dozen active volcanoes, more active than usual, I mean to say. As events come forward, there's some who are suggesting that this is related to the 9.3 quake that occurred in the Indian Ocean, creating the tsunami of December 26th. So now known as the Christmas Day tsunami. Now, is there any relation to the Earth's core and earthquakes, tsunamis, and volcanoes. Well, I think that's certainly one of the things we're going to discuss tonight, amongst others. And of course, you know that I have a keen interest in any correlation whatsoever to geomagnetic influence and its relation to the magnetic field, Earth's magnetic field, and is there any connection whatsoever to the Earth's core, and in part related to solar activity. Well, we're going to cover all of that. Let me tell you who is tonight's guest. It is Professor Gary Glatzmaier, solar physicist. Gary's recent research has focused on the Earth's core. He produced the first dynamically consistent computer simulations of the geo-dynamo, the mechanism in the Earth's fluid outer core that maintains the geomagnetic field. The simulation spans several millions of years using an average numerical time step of 15 days. At the surface of the model Earth, the simulated magnetic field has an intensity, an axial dipole-dominated structure, a westward drift of the non-dipolar structure that are all similar to Earth. Let's bring them on now. Professor Glatzmaier, are you there?
I'm here. How are you, Mitch?
I'm doing fine, and I want to thank you so much for coming on to the show.
Thank you.
Now, let me tell you how it all started, Gary. You were recommended by some heavy hitters, both of them working for directly with NASA and the European Space Agency. Now, at first I wasn't quite sure what the connection was, and it all started when a suggestion from Dr. Ronald van der Linden, director of the Solar Physics Department of the Royal Observatory of Belgium, which you may know, and now I'm seeing that that at one time your focus appears to be more as a solar physicist. As I look at your CV, was that one of your fields of study, Gary, before you turned your attention to the Earth's core?
That's exactly right. Yeah, I started in solar physics almost a quarter of a century ago, and then after a number of years working on computer models to try to understand the interior of the sun, I then got interested in the Earth's atmosphere, climate modeling, and used computer models to simulate the Earth's climate and what would happen under certain circumstances in the future. And then I got interested in the Earth, lower in the Earth, the mantle part of the Earth, which is the outer half in radius of the Earth, below the crust, and developed computer models to try to understand that. And then after that, I went even deeper in the Earth and made computer models for the Earth's core and how convection in the liquid part of the core generates the Earth's magnetic field. And incidentally, now I'm sort of moving towards other planets, and giant gas planets like Jupiter and Saturn. But the common thread with all these different problems is that my style of studying them is to develop sophisticated computer programs that solve the laws of physics, equations that describe all these effects, and simulate these things on computers and try to learn from what these simulations tell us.
Well, absolutely. Now, Gary, much of my audience is been following the show for quite some time, and so they have a general basic knowledge of solar physics, of geophysics, and so forth, and of course tonight specifically with the Earth core, but many do not. So I do want to lay a foundation here in just a few minutes of what your understanding of the Earth's core is. But before we even launch into that, I do want to read this very brief article that is challenging the idea that the Earth's core is fluid. Now, let me clarify with you first, Gary. In the introduction that I read, you mentioned that the mechanism in the Earth's fluid outer core. Is there a solid inner core?
That's right. Yeah, and we know this by the way seismic waves, sound waves, travel through the Earth. They're created on the surface of the Earth by earthquakes, and then these sound waves travel through the Earth and they're detected on the other side of the Earth. And the way we can tell the difference between what is solid and what is liquid is that a sound wave can be either a pressure wave, in other words, the pressure, I'm trying to decide the best way to explain this.
Well, let me ask you this, Gary. Are you familiar with something called the PKJKP?
Well, that's I don't know exactly what that is, but it's one way of describing a certain seismic wave that goes through the Earth's mantle and probably bounces off the Earth's core.
Exactly.
Yeah. But anyway, what I was going to say is that a sound wave will also be partly a shear wave. In other words, the material will move sideways as the wave passes. And this only works in a solid. In a liquid can shear and there won't be a restoring force, whereas in a solid there will be. So the bottom line is that the P waves, the pressure waves, will travel through both solid and liquid, but the shear waves only travel through the solid. So by identifying what type of wave you get on the other side of the Earth, and you have to do this for many, many earthquakes and piece it all together, people have done this many years ago. They can infer at what depth in the core is liquid and what is solid. So it turns out that the core, first of all, I should say, just to remind people that the core of the Earth goes out to about roughly half the radius of the Earth. And above that is the mantle. So below that is the core. But the core itself, the outer two-thirds roughly of the core in radius, is liquid. And the inner third is solid.
All right, let's go into the Dynamo Theory.
Okay.
If you could, give us an overview of just what that is, the Dynamo Theory.
Well, first of all, dynamo comes from the British word electric generator. And the laws of physics that describe how electric currents are generated in an electric generator are the same laws that describe how the magnetic field of the Earth is generated in the core of the Earth. Basically, whenever you have an electrical conductor, like a wire, being forced to pass through a magnetic field, what happens is that the electrons in the wire get pushed along the wire and you get electric current. But you also get a magnetic field associated with that new electric current. So in the Earth, you don't have wires and you don't have nice big magnets. What you have is all liquid iron that is moving, and it's moving in a special way because we call this convection, because the heat in the center of the Earth can't get out fast enough just by thermal conduction. So what happens is the material heats up, expands a little bit as it gets warm, and then becomes buoyant and rises to the top of the core, the bottom of the mantle. And when it gets there, it cools off, gives its heat to the mantle, and then it contracts and becomes heavy and sinks again. So this is convection, but in addition, it feels the Earth's rotation, in other words, Coriolis forces, because the fluid part of the core has what's called a very low viscosity. It's like water instead of molasses, for example. And so as this motion occurs, and the motion again is occurring because it's just transferring heat from the interior of the core to the outer part of the core. As this occurs, it feels the rotation rate of the Earth, and so it's not a straight trajectory. It's a very curved trajectory because of this rotational effect of the Earth. And this sort of, it turns out to be sort of a helical type motion, twisting and rising at the same time. And this motion tends to twist the original magnetic field into more complicated configurations, and in the process builds up a strong magnetic field. And the reason this has to continue to happen is that the temperature of the core is so high that you cannot have permanent magnetism in the core. In other words, the Earth's magnetic field starting in the core is not something like a permanent magnet on the surface of the Earth. It has to continually be regenerated, otherwise it would decay away. Now, it'll decay away roughly in about Well, half-life is something like 15,000 years. So within 15,000 years, if it were not being regenerated, it would be reduced to half its intensity and continue to decrease. And 15,000 years is a very, very short time compared to the age of the Earth.
Oh, yes.
And so it's been doing this for basically the entire history of the Earth, maintaining a magnetic field. And outside the Earth, it looks very dipolar, very nice and ordered. But inside the core, it must be very complicated and very intense. The dynamo, the geo-dynamo, is just a name for this whole process that generates the magnetic field by these fluid motions.
Gary, how similar is the Earth's core to the Sun's core? Now, the suggestion would be that the dynamo theory applies on the Sun, and I guess as you've turned your interest, your focus to other planets as well, are you looking for similarities to see if this causal effect, this mechanism, is the same in all celestial bodies?
Well, that's exactly right. It's the same principle, same laws of physics. It's the details are different. So on the Sun, in fact, I studied the Sun, the solar dynamo, long before I got interested in the Earth. And but the details are different. Obviously, it's a much bigger body. It's hotter. It's a complete fluid body. It goes from gas at the outer surface, and then it becomes a very, very dense gas in the interior. But there's no solid part of the Sun. Now, when you talk about the core of the Sun, what that means, it doesn't mean a hard core. What it means is that the interior part of the Sun, the radiation transfer, in other words, the transfer of heat from the interior to the outer part of the Sun, is efficient enough by radiation transfer, by photons moving from the inside to the outside, that you don't need convection. Convection doesn't start because nothing really heats up in any place and becomes buoyant. The energy gets out fast enough. And so the interior part of the Sun is called a stable radiative region, and it's sometimes called the core. But then you get to roughly about 75–80% of the radius out towards the surface of the Sun, and then all of a sudden the efficiency of these photons becomes smaller and smaller. In other words, the photons can't get out as easily as they did deeper down, and then all of a sudden the heat starts to build up, and then you get convection. So there is convection in the outer 20% or so of radius of the Sun. That's called the convection zone, and that happens there because the heat can't get out fast enough just by the radiation transfer. And so the outer part of the Sun is called the convective region, and the inner part is called the stable radiative region, or the core of the Sun. But the mechanism that generates the magnetic field in the Sun, the basic ideas, the basic laws are the same. It's just like I said, it's the details of exactly how and where the magnetic field is being generated. Those details are going to be a little bit different.
Okay, let me back up, Professor, back to the Earth's core. In what you said previously, I want to make sure I heard it correctly. Could it be said that the Earth's core is the creator, the sustainer, the initiator of Earth's magnetic field? Is that correct?
That's correct.
Now,
I mean, that's what we understand. That's what many people in this field, understand today. Is that that's where the magnetic field seems to originate from, and the most likely mechanism is this fluid motion generating a magnetic field.
All right. If that's the case, I'm going back to some very highly esteemed scientists, and you probably know some of them. Dr. Paul Breeke. He is the Deputy SOHO Project Scientist.
Okay.
Dr. Ronald van der Linden, as I announced, the solar physicist of the Department of the Royal Observatory, and Dr. Stefan Poots, lead scientist for plasma astrophysics, contracted to the ESA, European Space Agency. Now, all three of them, and actually it was Dr. Ronald van der Linden, as we were exploring some unusual spikes in the KP index, suggested that I might turn my attention instead of to the Sun, which is what I was thinking was the cause, but we couldn't correlate it with any sunspots or solar flares or CMEs, and he suggested that that it could be related to the Earth's core. And that's, matter of fact, I think he's the one who suggested your name to kind of look into this. Now, if the Earth's core is the perpetrator, it is the initiator of Earth's magnetic field, how could it not be affected in a larger way related to charged particles that hit the magnetic field? And when that happens, of course, it warps around the Earth as it protects. Does that not have any causal effect to the Earth's core?
Well, it certainly must have. I mean, I wouldn't say it has no effect. The question is, how much of an effect does it have? Let me ask you first, when you say the KP index, the spike in the KP index, on what time scale are you talking about? How long?
72-hour, maybe even less, a 48 to 72-hour causal effect. Now, that is specific to the spike in the KP index, the registered spike in the KP index to at least a measurement of 5, but usually 6 or 7. And within a 48 to 72 hours, I'm doing an outcome study which is appearing to seem that it's correlated perhaps with seismic and volcanic activity.
You're seeing a correlation between volcanic and seismic activity with these spikes in the KP index?
That's exactly what I'm looking at, yes, sir.
Well, that's interesting. And because my first reaction would be that 72 hours is a very short time to be able to see a change in something that originates in the core. The reason I say that is that things may be changing that fast, although let me say one thing. The fluid velocity, the maximum fluid velocity in the core of the Earth is probably about 1 millimeter per second. That's pretty slow.
Pretty slow.
So it takes about a year for the fluid to move 10 kilometers.
Professor, so you're suggesting that it's the shifting of the fluid that causes a plate tectonic movement?
No, not plate tectonic movements, but it's the shift. It's the movement of the flow. It's the flow of the fluid that actually will change the structure and intensity of the magnetic field slightly, and those changes could be seen at the surface of the Earth, but typically the changes occur over a long period of time, like months or years, there's something called the decadal change in the length of the day. It's something that occurs over 10 years or so, but so it's hard to imagine something changing in 72 hours. I'm not saying it's not possible. It's just hard to imagine.
All right, Professor, if I could, let me come at it from a different angle and explain how I even got to this point. My total focus was on, I have a book out called The Solar Rain, and it's the study of the Sun-Earth connection. And my focus was on how sunspots and solar flares, CMEs, are connected to extreme weather. I published a premise, an equation, that suggests the number of sunspots has an influence or a foretelling projection of the size of the solar event, such as a solar flare, the M-class, X-class flare, and a following CME, or coexisting CME, coronal mass ejection. Now, my hypothesis is that when those charged particles hit the Earth, the magnetic field would shift. When the magnetic field shifts, it shifts ocean and jet stream currents. And then when shifting ocean and jet stream currents occur, then we have these extreme weather phenomena. Now, that was my original focus. And then more recently, in the last couple of months, with the scientist that I mentioned to you, suggested that, in part, some of the geomagnetic influence in particular could in some way be connected with the sun, perhaps in the way of coronal holes as opposed to CMEs or solar flares, and these unusual spikes that are occurring in the KP index. And now I guess I'm suggesting or interested in, Professor, of other than the dynamics you just outlined, could there be any other way that the Earth's core in some way has some type of interface or interaction with solar activity in any in a very close proximity, like I'm saying within hours or a few days?
Well, what comes to mind is that if say you have an eruption on the surface of the sun and particles get shot out towards the Earth, and they, like you say, they disturb the Earth's magnetic field, the disturbance in the Earth's magnetic field far above the surface of the Earth, that's called the magnetosphere. The field is very weak there compared to what it is inside the core. But these disturbances will probably take the form of waves, what are called Alfvén waves. They're waves in the magnetic field. The magnetic field sort of acts like an elastic medium, and if something pushes it in one direction, it's going to try to respond and push back again. So you get these waves that can travel down the magnetic field and presumably into the core of the Earth. So I don't doubt that happens. The question is, the energy in those waves must be very, very small compared to the typical energy in the flow of iron that's got 10 times the density of water in the liquid core of the Earth. So it's the energetics that I question. But certainly everything's going to be connected. If you have a disturbance on the sun and that gets transmitted to the Earth's magnetic field, that's going to be, these waves are going to be propagating throughout the field and probably also, like I said, into the core of the Earth. If it's, those little perturbations may have some influence on the evolution of the Earth's magnetic field or vice versa. But
Professor, would one simple something that we could look at, some graphs that we could very quickly do an overview? Have you given any attention to the solar cycle? Let's call it the NASA's 11-year cycle. Is there any correlation to the solar maximum and more extreme activity with the Earth's core?
Well, none that I know of. People have been measuring the magnetic field of the Earth with satellites. And the current satellite is called Ørsted, that's circling the Earth and measuring the field all the time. To my knowledge, there's no correlation seen. Well, I should say this. It measures the field that it sees just above the surface of the Earth. And that field is going to be a combination of the field coming from the core of the Earth and also the field that's being disturbed. In other words, changes it sees will be partly due to changes in the field that's generated in the core of the Earth, and partly due to changes in the magnetosphere that are caused by the solar wind and the sun's magnetic field. So the satellite doesn't know, it records the changes, but it doesn't know where they came from or what caused them. I think most people assume that the changes that have a small length scale, like maybe less than 100 kilometers, or on the order of a few hundred kilometers in length scale, and time scales that are on the order of a day or more. Those things most people assume are related to disturbances or interactions between the sun's magnetic field and the Earth's magnetic field. In other words, magnetospheric phenomena. Whereas changes that occur on length scales larger than 1,000 kilometers and changes that occur over periods of 10 years, those things are usually attributed to changes in the core of the Earth. For example, over Africa, there is a sort of a imperfection in the dipole structure of the magnetic field, a little change in the direction, and that structure is slowly moving to the west over Africa. It has been for the last as long as it's been measured accurately for the last couple hundred years. It seems that this big feature is slowly moving over Africa. So that's attributed to the core of the Earth. But something with a very short time scale on the order of hours, I mean, I'm not saying it's not possible. It's just something that we could not explain as coming from the core of the Earth.
All right, a couple of now this question is it actually just came to me as we're having this conversation, and I have no scientific background for this whatsoever. But in the same way, Professor, that lightning often strikes, in other words, as I understand it, a lightning rod initiates from the Earth and goes upward, whereas so many of us typically thought that it was always a lightning bolt from the sky coming down. Using that model, does the Earth's the Earth's core contribute to events such as when power grids go out? Say it's a high, we're at the solar maximum, we're experiencing sunspot counts of 300, 400, M-class flares, X-class flares are occurring, say, and then say on an event of an X7 flare with a direct hit, is there anything at all that happens to the Earth's core at that time?
Again, the question is how much of an effect is it? And there must be some propagation. There must be some small magnetic wave type occurrence that propagates down into the core. But I mean, it's such a small perturbation compared to everything else that's going on down there. One thing to realize is that if you compute the total, I mean, this is based on our computer models, but it's probably pretty close to being right. If you compute the total energy, magnetic energy in the magnetic field, the Earth's magnetic field, more than 99% of that energy is inside the core. And what we see, at the surface of the Earth, it represents, less than 1% of it. So when you talk about that small, weak field at the surface or out in space being perturbed a little bit and sending, weak waves down into the core, physically those waves are going to cause some changes, but the changes are going to be so slight.
Okay.
Everything, the huge energy that's down there already.
When this type of event occurs, and so many of us are aware of just how damaging charged particles can affect us. We know of what solar flares and coronal mass ejections can do. Of course, the worst scenarios is when they knock out power grids. Is there any phenomena that comes from the Earth's core that goes upward to meet or interact in any way with this charged particles or perhaps even plasma fields? Is that still going back to your answer of, yes, maybe, but it would be so insignificant it would almost be non-measurable? Well,
now you're asking, are disturbances in the core being propagated upwards and interacting with fields above the surface?
Yes.
Okay, well, I would say that is also occurring, but those disturbances are very large scale, like over 1,000 kilometers in scale. And again, they occur on over long periods of time.
Yeah.
So I mean, you have to. I don't think there are any really small scale features, small scale disturbances that make it out to the surface of the Earth. One thing that happens, it's a sort of a shielding effect. Even if small time scale disturbances did exist in the core, and I don't know if they do or not, but say you had some little storm down there that produced something just snapped and you get a small spike in the magnetic field. Say that happened in the core. What happens is on top of the core and in the lower part of the mantle is saturated with iron, and so it's like a shield. Basically any disturbance there will be shielded from above, in other words, those disturbances have a hard time making it through the stationary iron that's on top of the core. It's the same thing like in a car. If you have a lot of magnetic fields being generated by the engine, and if you had if the frame of the car were made of plastic instead of metal, you'd have a hard time receiving. You'd hear a lot of static on your radio.
Yes.
And that's one of the reasons why it's nice to have a metal shield over the engine, so that you shield from those signals. So sort of same thing's happening in the Earth. So it's difficult to imagine. I'm not saying it's impossible. It's just difficult to imagine, based on my experience, that a small time-scale disturbance in the core would make it out to the surface.
Okay. All right, Professor, we have to take a break here, very short break, station identification. When we come back, folks, I'm going to ask Professor Glatzmaeir about Hollywood. The movie The Core that came out, of course it was Hollywood. We know how all that works. But often there are small pieces of factual information. So let's see if we can flesh that out. And also, yes, I know many of you are interested, we're going to ask Professor about the pole reversal. So stand by. We'll be right back. Don't go away. Welcome back, folks. For those of you just tuning in, you are listening to a live interview with Professor Gary Glatzmaier, who is a professor at the University of California, Santa Cruz. He's a professor of earth sciences, but at one time he had turned his attention to solar physics. He's also a solar physicist, and so he has a very good understanding of the sun as well as the earth. Who better to speak to about these things, especially related to the sun-earth connection. And for those of you that were listening to the first half hour, you can tell that I'm trying from every angle to see if I can confirm or corroborate some data that I'm trying to pull together, which I'll blame Dr. van der Linden for this, who had originally turned my attention to seeing if there's any connection whatsoever between activity of the Earth's core and the KP index, which measures geomagnetic activity. And so far, from Professor Glatzmaier, not, yes, Mitch, maybe a little bit, but I'm not aware of any causal effect, especially in the realm of hours, whether it be 48 hours or 72 hours or so forth. All right, fair enough. Now let's turn our attention to a couple of things. One is I'm interested in the Hollywood movie The Core, and I always, whenever movies like this, folks, come out, all the scientists that I know and researchers, their eyes just roll backwards, with disgust of what's going on because, of what Hollywood does to these things. However, there are always slivers of truth in some of these movies, so let's see if we can flesh that out. And, of course, I will ask Gary, about the polar flip or the reversal. Professor, welcome back to the show.
Thank you.
Excuse me. Now, I want to go ahead and start with the movie The Core.
Yes.
I have no doubt you saw it, if nothing else for a giggle.
That's
but
right, yeah.
Can you tell us what parts of that may hold true?
Well, it's interesting. About a year before, you can probably hear my dogs in the background.
Barely.
About a year, just sorry.
Oh, I can hear him now. Somebody must have just come over.
Yeah. About a year before the movie came out, Paramount Pictures called me up and basically explained the plot to me and asked me for my advice. And I said I wouldn't know where to start, because the idea was that if I remember correctly, what's happening is the inner core, the solid inner core of the Earth, was supposed to have stopped rotating, and then the premise was that was causing the magnetic field to decay away in a very short time, in a period of days or so, and then all kinds of catastrophe.
Yeah, celestial bodies were being sucked in. Meteors were coming right through. That kind of thing. Problems.
So, but I said, well, first of all, you've got the relationship between the rotation rate of the inner core and the magnetic field backwards. The inner core, and this is something we found in our computer simulations, and then seismologists have also seen this to some extent now too, is that the inner core, the solid inner core, which is sitting inside this outer fluid core, the solid inner core is probably rotating slightly faster than the surface of the Earth. I mean, very slightly faster. And if it is, the reason is that the magnetic field that's generated in the fluid core outside of it is pulling it along, like a motor, basically. Mainly because the fluid flow tends to be in the eastward direction on top of the inner core, and the magnetic field threads through both the fluid and the solid inner core, and sort of it wants to pull the inner core along with it. So I said it's not the inner core generating the magnetic field, it's the magnetic field that's causing the inner core to rotate. And then I said also that the time scale for the magnetic field to decay away, if for some reason convection in the fluid core stopped or became no longer efficient in generating the magnetic field, the time it would take for the magnetic field to decay to say half of its intensity is about 15,000 years, and not a few days. And when I told them this, they said thank you. Because they're interested. They were not interested in being scientifically correct. They were interested in having a little bit of science and catching people's imagination, and they couldn't come up with a good storyline that took 15,000 years. So they just sort of became a little artistic license there.
I understand. All right. Well, let me, because of our time, I do want to cover a couple of other areas. So let me get this one in, and that is the pole reversal, I guess is what it's most commonly referred to. And how is that related to the Earth's core, and just exactly what happens? Will the North Pole really become the South Pole?
Yeah, well, this has happened many times, hundreds of times in the Earth's history. We know this based on the magnetic remnants in various places on the Earth, mainly at the ocean bottom. The middle, for example, the middle of the Atlantic is a place that is spreading apart, and the reason why the Americas are spreading away from Europe and Asia and Africa. But it's slowly spreading apart, on the order of a centimeter per year or so. And as it rises, as new ocean floor rises from below, it cools and then captures the direction of the magnetic field that exists at that location at that time. So there's a record of what the magnetic field has been for the last almost 200 million years in the ocean floor. And there's also some records in lava flows. If a magnetic field were reversing at the time there was at a time when a volcano was going off, or there were lava flows, and once lava cooled, it will capture the direction and intensity of the magnetic field at that time. So based on all that information, it appears that the direction of the polarity of the Earth's dipole field has reversed many times in the past. But the typical time, I shouldn't say typical, let's say the average time between reversals is something like 200,000 years. But it's not periodic like the sun's magnetic field. What happens is that sometimes there may be as little time or as little an epoch as maybe a few tens of thousands of years between reversals, and sometimes there are many millions of years between reversals. And the reversal itself takes a couple thousand years.
Now, there are some who believe that we're at the cusp of something like that happening. In other words, basically we're due. Would you agree to that?
Well, it's a possibility. The reason people say that is that the satellite measurements of the magnetic field that have occurred over the last 20 years, 25 years or so now, show that the intensity of the magnetic field is decreasing. And so they say, well, if it's actually decreasing faster than it would if it were just decaying away. Now, when I said 15,000-year time scale, that's a natural decay time. But the field today is actually decreasing faster than that, and it would actually become very weak, say, in the next 1,000 years or so, if it kept decreasing at the rate it's decreasing right now. So that's why people, and what they've also seen in the record is that when the reversals occur, the strength of the magnetic field is very weak. Now, the converse isn't true, because the intensity of the field goes up and down, many, many times, and without reversing. And then once, in many, many attempts, it actually keeps decreasing, becomes weak, and then reverses. So we're in a state right now where the magnetic field intensity is decreasing, and maybe it will reverse in 1,000 or 2,000 years from now, or start reversing. And the reversal process itself will probably take about 5,000 years. So, that's a possibility, but it's just as likely that it won't. It's just as likely that it will continue to decrease for, say, another 1,000 years, and then start increasing again.
Let me ask you about that. There's a couple of buzzwords running around out there. One of them is the Schumann resonance. Another one is 0 point. And I think they were both relating to, well, the Schumann resonance, I think, is related to the vibration of the Earth, vibratorial frequency, of the Earth. And, well, let's just start with that. What do you know of this phenomena known as the Schumann resonance?
I'm afraid I forget what exactly that is. I imagine it's related to some vibration frequency of the core of the Earth.
Is there a measured frequency of the Earth? Is there a vibrational frequency that one can measure?
Well, it's probably.
Let's say like a hum.
I don't know about that. I don't know about that. I'm sure the core is moving in either vibrating or oscillating at many different frequencies. And so again, the question is that what is the amplitude of various frequencies? But it's not just one frequency that it can oscillate or vibrate at. So, but I don't know of a hum.
Okay. All right. Yeah. The suggestion was that I don't remember what it was. Maybe something like 11 hertz, or actually I don't know the measurements of the sound waves or frequency waves. But let's say it's 11. The suggestion was that it's gone down to 9, and that as part of the reversal phenomena, it actually reaches a point of 0, known as 0 point, or 0 point energy. I think it's related to 0 point energy.
I doubt if that has a connection with the reversal process. The reversal process, again, is connected to the dynamo. It's the dynamo. This mechanism of generating the magnetic field is something that is time dependent, and the magnetic field is changing all the time, but very slowly and in very disturbance in the fluid flow, like a little storm in the core of the Earth, that generates the opposite polarity magnetic field. And typically, this exists for a short time and then dies away. But once in a while, everything seems to be in the right place, and this new polarity starts to grow at the expense of the original polarity. And then maybe over a period of a couple thousand years, this new polarity is able to become larger and stronger than the original polarity and take over, and that's the reversal. But it seems to be trying all the time on a time scale of thousands of years, and most of the time it fails to reverse. But once in months and many tries, it actually it's a chaotic process. Once in many tries, eventually succeeds in reversing. So there's sort of two basic states, two different polarities. Either what we have right now is the magnetic field. The dipole polarity has a magnetic field that is directed inward at what we call the North Pole, the North Geographic Pole, and it's directed outwards at the South Geographic Pole. So what we have right now, and what has been the polarity for almost the last 800,000 years, is that we have a south magnetic pole, by definition, at what we call the North Geographic Pole. And it's a south magnetic pole because you take, this is all terminology, a compass needle, the head of a compass needle by definition is a north pole, and it's going to be attracted to a south pole. And it points to our North Geographic Pole, so that must be a south magnetic pole. But that, again, this is all the way people have defined things. But roughly half the age of the Earth, the reverse polarity was the case, where you actually had a north magnetic pole, where you have where the North Geographic Pole is. So you have these two polarities, and they're equally likely. And once in many tries, the fluid flows in the core of the Earth cause the generation of the magnetic field to switch. It's a very chaotic process. It's interesting to see it happen in a computer simulation.
All right. Professor, with just the short bit of time we have left, I want to turn my attention back to the Sun-Earth connection, and I want to ask you if you are aware, this was a press release that just came out 3 days ago. Are you aware of a research, or I guess they're calling it an experiment, called the LASIO-CIRID?
I'm afraid not. Tell me about it.
I will tell you about it. It's an experiment that they are going to use the International Space Station. They're working with NASA, and it's related to measuring earthquakes or seismology, and they're doing it by creating a huge antenna, basically using the Earth's magnetic field, or the Van Allen belt. I'll briefly read some of the description here to you. Monitoring these effects on the ground would require a huge global network of antenna. Fortunately, our planet has a natural version of such a net, bands of charged particles trapped in Earth's magnetic field called Van Allen belts. These belts are best known for shielding the atmosphere for cosmic radiation. Electromagnetic disturbances may be detectable in the Van Allen belts before an earthquake occurs, says Dr. Roberto Battistone of the University of Perugia, Italy, who's one of the coordinators of the study called the LASIO-CIRID. Professor, it sounds like, in part, the premise is the measuring of charged particles and its relationship to earthquakes. And could we take it one step further and say that in some way that's related to the Earth's core?
Maybe. It sounds exciting. If it works, it would be a great way to predict earthquakes and warn people. I would imagine what's happening, though, is you have you have some type of movement in the crust of the Earth, in a fault region where an earthquake is about to occur, and that must be generating some electric currents that are then detected by the spacecraft.
Yes, that's exactly what I've been. That's what I'm. That's
in the crust, not the core.
Well, okay. Let me ask you this: is there any correlation whatsoever, connection between earthquakes, seismology, seismic events, and the Earth's core? Is it any type of causal effect?
You mean?
Is it related in any way? In other words, is there the movement of the crust? Is that in any way related to movement of the Earth's core?
Well, I would say it's more likely that if you had an earthquake, that it might affect the field of the core of the Earth in a small way, but not the reverse. I can't imagine the magnetic field of the Earth actually, triggering an earthquake, because first of all, to get a magnetic force, you have to have a magnetic field interact with an electric current, and the currents in the surface of the Earth are not very strong, so the magnetic forces wouldn't be very strong compared to the huge viscous and stresses that you have in the surface of the Earth. So my guess is that the magnetic field of the Earth probably doesn't affect earthquakes, but maybe the reverse. Maybe if you have an earthquake, you might generate some current that might produce a magnetic signal that propagates downward, or you might change the moment of inertia of the Earth slightly because of the change in the position of a tectonic plate.
Yes.
That might change the rotation rate a little bit, and that would have an effect on how the Earth's magnetic field is generated. So in other words, I would say that it's more likely that an earthquake might have some small effect on how the Earth's core in the geo-dynamo is operating.
All right. We've just got a minute and a half left, if that. And Professor, I don't know if you had a chance to see the movie on the Discovery Channel called Super Volcano, but it was fantastic. A touch of Hollywood is in there, of course, or actually probably a lot of Hollywood. But no, I'm quite familiar with this particular discipline. Matter of fact, I did an investigation reporting with the USGS itself on some rather peculiar misreadings by the USGS and seismic activity around Yellowstone. And that's what the whole movie is about, is Yellowstone in particular, the Yellowstone caldera, sometimes known as a supervolcano. My question to you, Professor, is there any connection between Earth's core activity and volcanism?
I think I have almost the same answer. Again, the forces involved in volcanism are huge compared to the magnetic forces from the Earth's magnetic field. So again, I'd say it's difficult for me to imagine how the Earth's magnetic field could affect a volcano. But the other way around, there may be some connection there. A huge volcano causing lots of magma flow, causing its own earthquakes, may have a small, effect on.
At what level, Gary, are the magma chambers? Now, some of us, until we start to study a little more, actually thought that there was a direct channel or a chamber that went a volcano. If we went to Mount St. Helens and we looked down down the face of the cone, we would see the middle of the Earth. Can you tell us how that all works out? Where is the magma?
Oh yeah, the volcano and the magma chamber are in the crust of the Earth. They're very close to the surface compared to the core of the Earth. There's a huge mantle between where the magma chamber is and the core. So there's no connection there. The core is liquid iron, but the magma is not. The magma is melted silicates. In other words, the magma is melted mainly because there are tectonic plates that are subducting under state of Washington and Oregon, because of all this frictional heating that's occurring, but it's occurring probably less than 100 kilometers from the surface. So it's still what I would call more of a crustal or surface feature with no connection to the core.
Okay, one last 20-second question. Actually, I'm already over time. What happened to Mars in any way whatsoever, assuming that there was a life on Mars, maybe a living planet just like Earth or similar to Earth? Did anything happen to its core that contributed to becoming a dead planet?
Well, that's an interesting question. Some people will say that, first of all, the big difference between Mars and the Earth is that Mars is much smaller, and therefore it's going to cool off more quickly. And so, as I was mentioning at the beginning of the hour, the reason we have a magnetic field in the Earth is because the core and the center of the Earth is cooling off and driving convection and moving fluid around and generating a magnetic field. This probably happened in the beginning for Mars, but then it cooled so fast because it didn't have to. It was a smaller planet. It cools off faster, and the heat didn't have as far to go to get to the surface. And as it cools off, the inner core solidifies, and pretty soon the fluid core becomes smaller and less efficient, and at some point it's no longer going to be able to generate a magnetic field fast enough to replace the part that's decaying away. So I can imagine that at some point early in Mars history, its magnetic field just died away, and once you have that die away, you get more cosmic radiation in, and maybe it helped remove part of the Mars atmosphere, although Mars has a hard time keeping an atmosphere like the Earth too, because there isn't as much gravity. The mass of Mars is much less than the Earth, so the atmosphere has a harder time, or it has an easier time of escaping from the planet. So it's hard to say, and that's a big question many people are working on. What was Mars like in the early days?
Oh, one quick last one. I'm getting all these emails, but one that's, and this is kind of actually I'm interested too. What would happen if a 10-kilometer asteroid hit the not to the surface? What would happen to the Earth? Would the planet die? Not life on Earth if a 10-kilometer asteroid hit like the one in the Yucatan, but is there anything that happens to the Earth's core that could maybe have the effect of what happened to Mars?
You're certainly going to have a lot of problems on the surface of the Earth, but yeah, a 10-kilometer impact would probably affect a lot of the top of the mantle. In other words, melt a lot of it, and certainly produce a huge shock wave that would propagate down into the core. It probably would change the moment of inertia, in other words, change the rotation rate of the Earth. But I'm not an expert in impact, so I don't think. I guess it depends on how fast it's coming in and what it's made of. But I doubt if it would actually get down to the core and actually break the core apart. But it probably doesn't need to in order to make a big difference. So it probably could affect the magnetic field in its evolution, an impact like that. But the details.
Okay. The things we think about.
Yeah.
Professor, it has been a wonderful interview, and I'm lucky to have you on as a professor because you were able to discuss with us in terms that we can understand, and you definitely have a wonderful delivery. The professorism comes out in you. and I'll tell you, sometimes when I interview some of these hardcore scientists, it can be very difficult, but that was not the case tonight, and I want to thank you for joining us.
Thank you. I appreciate it.
You're welcome. Bye-bye.
Bye.
Boy, do I have a lot to think about and write about, and of course I'm going to bring you in on this. And folks, wait till you hear more about this Lazio-Cirid experiment involving the International Space Station. the Van Allen belt, measurement of geomagnetic flux, and prediction of earthquakes. Now, is that fascinating? And this is coming from a scientific body out of Europe. So more on that later, folks. I got to run. Like so often, I am. Oh my gosh! Don't even tell me how far I've gone over. This is Mitch Battros for Earth Changes TV Radio Hour signing off. Look for my report on tonight's interview. You're going to want to read this one. Take care. Bye bye.